Welcome to today's webinar with the title Impedance is for everyone. I am Andreas Schilp, your host of today's Wirth Electronic Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is Andreas Dreher from our Technical Project Management. Welcome back, Andreas. And now I wish you lots of fun and new information.
So a warm welcome also from my side. A quick introduction for myself. I'm Andreas Dreher in the Technical Project Management. I'm since 2003 at Wirth Electronic and started my career in the lab. I've done a lot of investigations in base material, qualifying new processes and machines. And nowadays I'm in the HDI and signal integrity part and helping you finding nice solutions for your boards. Today's agenda is impedance. We will go through the introduction, what is impedance, where it comes from, why is it important. We will have a look especially in the whole agenda on design of manufacturing, so what we can do in building the boards in a very good way, and sometimes also some careful thoughts what you should avoid. We will discuss with stackups, we will have a look in high-speed materials, and on the final part a little bit of best practice, what is working on other projects and where you have to be careful on avoiding pitfalls. So let's jump directly into the topic. And if I see this whole picture, this whole point on impedance discussions, I see this gear system in my mind, in my head. You have the different stack-ups, you have technology selections, design rules. Sometimes you have a price target to meet, so effort in the build-up is also very important. And where to start? Where to start in such a complex system where all the components are interlocked with each other, and if you move on one part, you will move the whole system in some direction. Typically, it starts really early when you choose the actual component. So that's really the most important decision and will lock a lot of features in the following session. We will come back to this slide through all of the presentations and have a look on it. So the component is giving you usually a data sheet. In this data sheet you have some impedance requirements. With the fan out, as more complex, as more HDI the board is, as more technology we have to use on the PCB side. If you need a lot of layers for the fan out, the stack up is heavily influenced. So really the whole system starts by the component choice, and if you do a good choice there, you will have also a good and reliable board. If you made a critical choice here, it can go the other way, and maybe the effort in building the printed circuit board is pretty high, and you have to pay for that choice later. So that's really important to remind. And if we go now into the impedance, what is impedance? Where does it come from? The impedance itself is the AC resistance of a conductor. Can be a wire, can be a board, can be a component. So if you compare it with a DC application, you have the standard ohms resistance, and as higher the frequency gets, as more the impedance takes over, and you have to use this value for the conductor, and it starts around to get a major influence factor at least above 200 megahertz, so really early, and then you have to think about impedance into your whole design, your setup, and also your components. Today we have a lot of different ways to get the impedance, and I took the IPC formula as a simple stack-up, and I thought I start with heavy stuff in front, that we get more and more easy stuff at the end. So this is the formula to do a simple calculation of a surface microstrip, and let's go quickly through it and get some ideas what does this mean for us in the practice. So we have the target value, in that case the Z0. This is the impedance value which we want to calculate. We need for this calculation the epsilon r. In math it's often the epsilon r value. In the datasheet it's often labeled dk for dielectric constant. It's the same. The 1.41 is some magic number from the formula, also the 87 natural logarithms here, also magic number, everything in the books. For us, important is the height of the dielectric, the width of the track, and the thickness of the track. These 4 parameters in a simple microstrip calculation is necessary to make the calculation, and if you have a little bit advanced calculator, you can actually do it by hand. So it looks complicated in the beginning, but it's still possible to do it by hand. Of course, in the real world is not so easy. Let's skip one slide and go back afterwards. We have a lot of different options. I've showed you the simple version. You can have differential pairs, you can put them on the inner layer, you can use different materials, and of course it gets more and more and more complicated, which makes it hard for us to find a one-fits-all solution. With my experience, I'm pretty convinced there is no one-fits-all solution. We have to find individual solutions for everybody itself. The layout is influencing, the component is influencing, sometimes the price is influencing. So if you need a impedance controlled stack-up, feel free to contact us either with your usual sales contact, or you can contact us on the shown email address, and we will find a solution with you together. Coming back from the heavy math to the more graphical diagrams, I prefer this much more because it gives you a strong indication to show what is influencing on what matter. For example, the track width, it's has a high influence. It influences the impedance. As wider the track gets, as lower the resistance will be. Similar thing with the dielectrics. As thicker the dielectric is, as more the impedance will raise. The copper thickness, for example, has a low impact. It will not change it very heavily, which is actually pretty good, because usually the copper thickness is with, for example, IPC reliability requirements. If you have IPC class 3 with 25 microns copper in the via, the copper thickness is already locked in, and you cannot use it as a free parameter in your design choice. So most of the time we work with the track width and the dielectrics. If this is not enough, we can change the dielectric constant by changing material, either the pre-preg or the whole replacement, and using a more suitable high-speed material. But this, as we learn later, is really a big step influences a lot of factors and has to be really carefully considered. It is possible, but it will be usually very costly. So, to give you an idea here, there's a wide variety of impedance requirements. Very often, an impedance calculation is enough. You have your requirements usually from the component datasheet. We sit together, create together a fitting stackup, make an impedance calculation, take in consideration that material selection, design rules, and also a little bit on the process tolerance, that we have a good stable setup to make a high yield production later. Sometimes the impedance measurement is necessary to check is what we have in the calculation or in the simulation thought, is this also working in the real world? So we have to add test coupons next to the production board and we measure every panel in the production. And then we have here a process control, is everything we put in also at the end in the final inspection in the impedance measurement, was it achieved? And for more and more advanced boards, the high speed signals gets faster and faster, so the requirements also grow. Sometimes even that is not enough. We have to go really to high speed measurements. We have as the only supplier in Europe, we can measure boards in our facility up to 40 gigahertz. Again, we need dedicated test coupons next to your production boards. Then we can measure not only the impedance, also the decay value or the loss factors, for example. It's a very important research and development tool. The effort is higher than the standard impedance measurement, so it's maybe not a very effective process control because the effort is so high. But especially in complex projects, it is useful to have here real measurement data to check the datasheet values in the beginning. So this is a quick introduction. What is impedance? Why is it important? What is the main influence? Let's go in the design of manufacturing points with a stackup. Coming back here, if you choose a component, the technology and the stackup is directly influenced. Let's go in a real-world example. You have used a BGA with a pitch of 0.8 millimeters. This is sometimes possible to do in a mechanical fan-out. You don't need HDI. You can use it, but there are sometimes options to make it cheaper. Now this component is not available anymore. You have a successor component, and in worst case scenario, the pitch is only 0.4 in a successor component, and then it is not possible to do a single stack-up. You have to use a very complex HDI example. This example is of course extreme, but it shows you the pros and cons of both worlds. So the component gives you the need for some HDI layer. The HDI layer defines as the prepreg thickness. Not every prepreg is possible to laser drill, especially very heavy glass fibers like the 7628. It's not possible to laser drill it. So you have some fixed points here in that point, and we have to consider this in the impedance calculation. How do we build such a board? For your reference, you will get the slides afterwards. Here are the labeling, but for speeding up in time, we will skip over it and go directly into the production. So we start with a 6-layer in the beginning, in the middle. Press it, drill the buried vias, fill them. In that case, it's a type 7 filling with a cap on top of it. Then we add on both sides together a new prepreg, go back to the pressing, press the prepreg to this board, go to the laser drilling, drill the microvias, make a copper filling, and repeat and repeat. So we have to go through several steps in our production. In that case, we have 4 press cycles, 5 photo processes, and 6 galvanic processes. And of course, it should be natural that when the delivery time is going up, a standard board, a standard 8-layer board, has only 1 press cycle, 2 photo process, and 1 galvanic process, and you have some delivery time. If you now go 4 times through the press, of course, the delivery time must be higher. So for us, very important, usually the stackup is symmetrical. If you add something on one side, you do the same thing on the other side. If you don't do it, you get warping, for example, in your soldering process, and it's not good for us and not good for you or your EMS. So we love symmetry here. Also, the technology choice, if you have a small pin-out, staggered microvias is a feasible option. You can fill them on the outer layer for enhancing the process window in the soldering process. In that case, we have a resin filling type 5 in the microvia, because on this board there are some buried vias. It's not necessary, but also not a bad thing. Usually it's enough to fill with a pre-preg resin the microvia here in the press to avoid any voids. But in the case of a 0.4 millimeter pitch BGA with a high pin count, you have to go the stacked microvia way, because you don't have the footprint space in the board. So you have to do the microvia filling on every layer. You can save space, but it's more effort in the production, and more effort means more money. So this all is affected by the component choice. A next point, also a very important one, is the etching of every layer. How do we etch? Usually inner layers, for example. We start with 100% copper. On the board we want to have some differential pairs shown in the right hand corner, and we will laminate a blue etching resist again on a full frame. We expose it with light, wash away the non-exposed areas, and then we have etching resist with some openings in between. We use now some etching agent. We are spraying them onto the surface, and for every micron we etch to the depth. As soon as the sides are exposed, we also etch to the left and to the right. So if we etch 1 micron deep, we etch 1 micron left, 1 micron right. So for every micron depth we have 2 microns to the side. And if we etch on and notch on, here's a picture from a machine, this typical pattern of a trace is formed. And this is very important because the copper thickness is affecting the space in between. As higher the copper gets, as more space we need by physics. It's not our choice, it's just physics, how the etching is working, that we need here some space. We have some design guides. These are available on the homepage. Again, as thicker the copper is, as more space you need in between the conductors. For us, it is easier to make narrower traces, to narrow down the line width, as long as we have enough space in between. So this is very important also later for the impedance calculation, because if you have some technology combination, like here shown a buried via with a filling with a type 7 cap on top, every line you see here is a galvanic process, and as more we have to go through the galvanic, as higher the copper gets. And what we learned now, as higher the copper is, as more space we need. If we have not enough space, we have here a picture which is showing what happens when it was not enough. It is a heavy short. This will sort it out in the electrical testing. But if you only have a 1 micron etching more, It's not a short anymore, but it will be not good for our impedance calculation. So here, very important to find optimal parameters in the impedance setup, in the line and space width, to make a good reliable board that you can avoid such cases, which is layout influenced, very important, influenced by layout, to consider this point. So coming back on this slide, we discussed if the copper thickness is high, we have a low influence on the impedance, which is good, but we have to consider the spacing in between the tracks. So the whole calculation is influenced, and we have to compensate a change on this point with the two other options, usually by track width. So what is the best combination, you maybe ask? Here I have several examples. Everyone has exactly 100 ohm differential impedance as a differential pair. And in that case, I increased the width of the track, and the distance between the track is pretty low. And that's what I explained. If the distance is pretty low, we have a hard time of etching. Yield goes down, price goes up. So this is maybe not a good combination. So okay, let's increase the distance between the tracks. To get the same 100 ohms, we have to lower the pre-preg thickness and also lower the track width. Maybe you have some dielectric high voltage requirement that you don't want to have such a thin pre-preg. So what to do then? We can find some parameters in between, or sometimes you have an input that you have a high copper track because maybe you have some high power components on the same board. And then again, you have to compensate by adjusting all the parameters. So is there any best combination? With my experience, I would say no. It depends on your requirements, on your layout, on your components, and we have to find the best combination individually. So let's jump into high-speed materials. What is going on if we can find a good impedance solutions only by the dielectric and the track width, for example, if we have to change the decay value of a material. So what is material? As a quick starter, we have usually double-sided coated copper cores and prepregs. They are made, of course, with copper. They have glass fibers included, and there is also some resin to glue everything together. Let's go through it step by step. First, of course, the copper. That the copper is sticking to the plastic, to the epoxy, for example. It's very important that we have some kind of roughness. Every copper foil has a treatment and a shiny side. The treatment side is usually to the inner of the core, and as higher the copper is, the copper foil, as more rough it is by nature. It's in the construction process of a copper foil, as more copper you have, as rougher the treatment side is. And of course, the other side is the so-called shiny side, because usually it is shiny, it's pretty flat. And if you want to glue some metal to plastics, and if it's really soft and shiny, it will not stick very well. So we have to roughen up by etching this shiny side and add also an adhesion promoter. If you would do some painting, often this is primer called. We have a similar thing in the PCB setup. So even here we have to rough up the copper and create some roughness. Why to care about this point, maybe you ask? There's a physical effect called skin effect. And as a simple explanation, as higher the frequency is, if we look, for example, on a wire, in a low frequency or even in a DC option, the wire is totally used. The whole cross-section is used up by the current flow. And as higher the frequencies get, as more the current flows only in the edge of this conductor. And in a worst case scenario, at a very high frequency, it's really only the skin of the wire. If we compare that to a trace, if we will feed some current through a trace, it will not flow the direct way, which we usually expect, but current is always taking the shortest and easiest way, not in high frequency area. It's really going through every rough thing, because there's also a so-called proximity effect. Usually we have the ground layer underneath, and the current is also closer to the ground layer. So as more rough the copper foil is, as more skin effect we have. And if you want to learn more about skin effect, I'm sure there are bookshelves full of information and books and seminars about it. You can fill a whole week just with skin effect. So let's keep it in this easy, simple way. But it will definitely affect our loss factor. It will definitely affect the speed of the signals. So it will also affect a lot of parameters here. So and if you are higher than 3 gigahertz, the skin effect is taking more and more in account, and you have to think about it. If you have a really high frequency board, let's say more than 10, 15 gigahertz maybe, sometimes it's necessary to use dedicated low profile copper foils with less roughness, but of course less roughness means less adhesion. So if in a perfect world, we would use a completely flat copper foil, but you can just peel it off from the board and you cannot solder any components to it. So again, a compromise have to be found here. If we look on a pre-preg, on the glass fibers into the board, there are several cases, and this is just a short extract. I'm sure on the market we use typically 20 different styles. They are labeled usually with names like 106, 1080, 7628, which is maybe one of the thickest one, and usually not used in high-speed boards because the parameters are not optimal for them. Usually it's the other ones, and many more, just as a reference example. And an important thing here, we have two different materials, at least two different materials inside. We have the glass, which has a typical value of 6 in a epsilon air, and the resin itself in a FR4 board has 3 point something. On the data sheet you find different numbers because you see a summary of these two numbers, and if the resin content, for example, changes either by design choice or your layout, of course, influences also the resin content after pressing, the parameters will shift a little bit. So I'm sure all the datasheet values are correctly measured and can be trusted, but the layout will influence this value again, and so we need some experience to feed in the impedance calculation that we know with this typical layout or another kind of layout, we have later a typical resin content of something else, and then the decay value changes. Again, a short extract. We have made roughly a year ago a dedicated high-speed seminar about our physical hand sample, and there is a fiber weave effect where these parameters will influence. For example, we have a differential pair going, one is directly on top of a glass fiber, the other one is directly over these holes where you have 100% of resin, and this is disadvantage. The parameters will change. The speed of the signals, the runtime of the signal also will be influenced. So what is a good option? You can tilt the whole board, your design, in our production panel by 10 or 15 degrees. But this lowers the outcome, how many boards we can produce at once, so the costs will rise. Maybe you have only a few signals, so can go with this zigzag routing and only the most critical signals can be in this zigzag pattern, that you have a mix of all the parameters, and then this is even out. Usually such a case is important at frequencies at 20 gigahertz and higher. Most of the customers are not in this area, happily, because if you want to design such a thing, most systems did not support it. They are working on it, but it's not implemented yet, so you have to draw such a pattern by hand. If you need help with such a thing, if you want to create such a simple thing, we offer you as a service. We have a small design team which can help you with this thing. You send your board in, we draw these boards, these traces, and send you the data back, and you can go on. If you need assistance here, feel free to contact us. So in the last part of material is the resin. And for the high-speed properties, the resin has a very big influence. We come from the good old epoxy resin. For the last 50, 60 years. We used in most of the cases an epoxy-based system. Different TG values are available. Typically the parameters of dk and df. df is the loss factor. It's around 4 point something, 4.4 for example. And you can get them with or without fillers. Every supplier, raw material supplier, has nowadays a so-called mid-performance material. Our choice was Panasonic Micron 6. It uses a different kind of resin, so it's not epoxy anymore, it's a PPE resin system. We have a TG at 155. The decay is very low compared to the standard raw material, and also very important, the loss factor. Don't get mixed up by this 4. He has a 0 more in between, so the loss factor is pretty low. You find still in a lot of application notes on components Rogers material as a reference. Rogers had a good start very early in the beginning of this high-speed development. They offered good performing material. If you compare the values, they are pretty similar to these values nowadays. And most of the high-speed parameters are influenced by these ceramic fillers. They differ from the other fillers used in the other material, and we will come back on the next slide why this is important. So what does it mean in a production of a PCB when we change the material? We have to use different raw material, and the raw material itself has a pretty big impact on the total cost. Depending on the material choice, it's ×4 to ×20 more expensive than a standard TG150 material. With the changed resin system and the higher TG values, we need more aggressive chemistry to get it clean. For example, after drilling, you have some debris in the hole, you have to desmear this debris, and there we need more aggressive chemistries, higher temperatures, longer exposure times, which adds on cost. Also affected by the TG, the multilayer pressing itself, you need higher temperature, you need more time. Time means money. So you have also an influence here. And with the drill parameters, if you take a 0.5 millimeter drill bit, in a standard material, it can drill 1,000 holes. Then you can take the tool, resharpen the tip, and use it again. So in its lifetime, a standard drill bit with TG150 material can drill 3,000 holes. And if you use, for example, a Rogers material with these ceramic fillers, the drill bit can only drill 100 vias, and then the tip is so blunt, and also the edges, the sides of a drill bit are affected, that the diameter is changing, but we cannot use this drill bit anymore. So if you have a complex board with a lot of stitching vias and every drill bit can only drill 100 vias, you can really calculate very fast how many drill bits we go through. And of course, every drill bit costs some money. and the cost have to be shared. So changing the material has a lot of heavy impact. If you have a good material choice, a mid-performance material with similar parameters is not so critical in drilling, for example, as if you use some ceramic fillers and have still similar properties. So this is very important if you can change here the material. We have a lot of materials qualified. Today our go-to material for high-speed applications is the Panasonic Mectron 6. Shortly we have a Mectron 7 also available. We can also do the Rogers material if necessary, and also our partners in Asia have a lot of materials available to get you some ideas. We have this nice physical samples, which is really a good starter to get introduced into the material. You can order your sample for free on the shown address. There's a lot of information available. We have also shown how to make the impedance calculation on this stackup. Again, not as a copy and paste solution, just as an idea, as a starter to show you what is the options with this material. If you need a solution for you, feel free to contact us either with a shown email address or with your usual sales partner, and we find a solution together. Very often also in the discussions about high speed, we get the requirements about backdrilling. So what is backdrilling? Backdrilling is usually if you have a via going from top to bottom and you only need the connection from, let's say, top to layer 3. Then the rest of the via acts like an antenna, can get some strange signals from outside or from crosstalk, and can mix up your signals and make your signal integrity worse. What was the solution from the past? Drill the via away, drill them back, and get rid of the stub. This technology was invented before HDI microvias was available. Today we have microvias, very reliable, very widely arranged. So today it's very easy to find an HDI solution. It's cheaper, it's faster, it's more reliable instead of doing back drilling. So if you need something with this, really consider going for an HDI version. Even if we can do back drilling and off-it, but it's a lot of effort. Also in this sample, a nice idea, which is not much effort in the production. To give you some idea, we can do such metallized shape. So we do a depth milling before the galvanic step. When we have an edge metallization in the etching, it's also not a lot of effort. And then you have, for example, in that case, a waveguide where you have a shield on the both sides on the ground, and maybe you solder a lid on top, and then you have 100% shielding all around with not much effort on a PCB side. So this is really to give you some ideas, be creative, to have here nice solutions. So, and last point in our presentation is the best practice part. Let's jump in. If you have a fine pitch component, like in this area, you often need very narrow spaces and also small conductor spacing. But outside, if you have other components, please give us some wiggle room, give us some space that we can achieve also a good yield. So if it's narrow, yeah, you have to use small, but please give us some spacing in the other area. Also with the same footprint, typically the definition is, for example, 100-100, so a symmetrical definition, 100 line space and line width. But why not use 80 line width and 120 space? Makes us the production simpler, easier, higher yield, lower price. For you, it's the same footprint, and often if it's only a signal, the 20 microns doesn't matter in the signal properties. Also, a customer has to change the component. The 0.8 pitch component was not available. He don't want to do 100% redesign of a board. The new component had a pitch of 0.5, and he was using the same impedance calculation. So in the new design, the distance between the track was not fitting anymore. So he had to change something. What has he changed? Yeah, it's very easy. Just shift the tracks away, that you have the same spacing, which was also the correct one for the old impedance matching. But now the signals are so close to each other that you have between the two different signal sources a crosstalk. And this should be avoided. You will really mess up your signal properties. And usually it's very hard to find if the layout is done, and if you measure the performance and you see the performance is not there, you have to invest a lot of effort to find such problems and fix it afterwards. So we found a solution with him together. We have to add microvias in that case, put the signal 2 onto the inner layers, and problem was solved. So here, best practice is really a good thing. With flexible stackups, of course, a separate calculation for the rigid and the flex part is necessary. And we recommend, for example, in the flex area that you add such a crosshatch pattern, that the drying is better and faster and you avoid delamination. But if you have a differential pair above these structures, again, we have seen this fiber weave effect. It's a similar effect. You don't have a closed return path, which is really bad for a signal. The impedance simulation can simulate it. You can adjust your parameters to it, but maybe you can just use a closed ground layer here just in this area where the tracks are, and around it you still the crosshatch pattern. The drying should be still okay, and your impedance signal is more stable, more reliable, and gives us in the whole tolerance section more wiggle room. Also talking about tolerances, a very important step. The Polar software has the nice option of a Monte Carlo simulation. So you use your properties of your design, and you can feed in some tolerances. For example, typical process tolerances or the IPC worst case scenario, what is available. And then the software is doing 1,000 iterations, for example, and doing a calculation with all different options, if and when, and so on. And then you get such a graph. What does the graph shows us? The target impedance, again, was 100 ohm differential pair. 100 is somewhere here. So if we have a look on the total graph, the whole graph is right shifted. So in most of the cases, even if the standard calculation which you do is exactly at 100, if you have the typical tolerances, the whole thing is more in the area of 103 ohms, which is inside the tolerance but not a tight fit. And sometimes even you have some extreme options inside the IPC tolerances by the layout, but outside of a typical plus minus 10% of the impedance calculation, even if all the parameters are inside. So this is the point where you really need experience and have to find a best fit solution for your layout that you can avoid such a shift, because the math is right, it's exactly 100. But in the real world, you have a drift, and this can only be compensated with a lot of simulation or with a lot of experience in PCB production, which we have. So coming to the summary, how to approach a completely new design. Either you have the experience and you can use it, or you have the components to do all the maths. You can go trial and error, order some prototypes, measure it, fix it, order the next prototypes. but then what is time to market? Can you do simulate before fabricate? Today there are a lot of tools are on the market, but very often the licensing of the tools is very expensive. And as later you recognize such a failure and you fix it, as more time and money you have to invest to fix the problem. So what can be a good approach? You do a planning, we do together a good impedance controlled stackup. We find design parameters. If you need assistance with a design, we are happy to help you with a design team. We can do a feasibility check, give you some feedback in the EQ process to optimize it further. In the production, we have a lot of quality control. Sometimes, especially with antennas, a design-in is necessary. That's the more or less trial and error part. And at the end, we can test the parameters to really see on every production panel that we achieved all the calculation and planning. So as a final slide, we have qualified high-speed materials in Germany. We have a lot of partners in Asia which can support us with different materials. We can measure material and layered parameters with a polar system. We have a lot of experience in controlled stackups, and definitely the high-speed design is very complex and it's hard to squeeze a lot of information in this time frame in. So if you have any questions, feel free to have a discussion with us on your design. And with that, we are on the final slide. Thank you.